Great. So yeah, and also let me know if this is I'm going too slowly. Um, okay, so let's see. So we were just talking about the covariance and regression coefficients. There's a lot more to be said about both of those things, obviously, but we've said what we need to do for the purpose of deriving the price equation. Okay, so so here's what the price equation deals with. Okay, suppose you have a population, and my population is going to be it's going to be a population of birds. Here are some birds. Okay, these are the theoretician's birds. I don't know what species. Don't ask me. Okay, so you have these birds. Okay, and I'm going to call this population this population of birds the ancestral population, or the ancestors. Okay, and then I give you another population of birds. Okay, and these are little birdies that make up the descendant population. Okay, and I'm going to call these ancestors and descendants because that's one way these two populations can come about. So one of them actually could be the offspring. So the descendant population can be the offspring of the ancestor population. Descendants, or descender, anyway, descender population. But in fact, these are any two population will do actually, right? The only thing that you need is you need to be able to assign each of the descendants to an ancestor. Okay. So in this case, I put these two guys together. I said these two guys are the descendant of this guy. These two birds are descendant of this bird. This bird is descendant of this bird. Okay. And obviously, so if these were actual birds, you would have to actually have two descendants, right? Because birds are sexually reproducing diploid organisms. So each bird has a mother and a father. But we're going to ignore that detail for the moment. That detail for the moment. We're just going to pretend each bird has only one parent or one ancestor. Okay, and of course, this could be literally true if we're talking about haploid organisms or selfing organisms, right? In this case, it's not literally true, but you can account for sort of multi-parental inheritance or descent quite easily. Actually, it just makes the notation a little bit like more involved. But otherwise, it doesn't change anything significantly. So for ease of exposition, we're just going to pretend that every single descendant has a single ancestor. Okay, but every single ancestor might have 0 or 1 or more descendant. Okay. And in fact, you can also incorporate things like migration, where the descendant is not descendant from any of the individuals in the ancestral population. It's migrated into the population, so there's no ancestor for the descendants. So you can even incorporate things like that. But we're going to write the simplest case. Okay, so so the price equation describes evolutionary change, we said, or change in a trait or phenotype that you can measure. Okay, and we're going to measure the phenotype. We're going to call the phenotype phi. Okay, and then each individual in the ancestral population will have a phenotypic value. Okay, so this could be like, how their weight, for example. Okay, and we're going to call them phi 1, phi 2, phi 3, and then each descendant population. So this is the ancestral population. In each descendant population, we're also going to measure the individual's traits. So they all also have phi's. Okay, but because now for notational convenience, we're going to keep track of the descendants by labeling them first with their ancestors. So first offspring of the first ancestor, right? First descendant of the first ancestor, so phi 1, 1. And then, you know, so first index will be their ancestor, and the second index will be sort of whichever descendant they are. So first descendant or second descendant, okay? So this guy would be phi 2, 1, okay? And this guy would be phi 2, 2. This guy would be phi 3, 1, and there's no phi 3, 2 in this case, okay? So that's just notational convenience. And in fact, the way we're going to write down this phi, I mean, and once you measure all of these traits, okay, and again, I'm going to emphasize this has happened, okay? So you had this ancestral population, and then you have the descendant population, okay? You measure the phis of the ancestral population, and whatever they did, and produced however many descendants they produced, and then you end up with the descendant population, and you measure the descendant population traits, okay? So everything has happened here. We're not trying to predict anything, okay? Everything has already happened. We've measured everything. We're just going to write down the change in the mean phenotype, okay? And to do that, we're going to actually write down phi 1, 1 as it's the ancestor's phi, okay? So this is the first descendant of the first ancestor, okay? And its phenotype is going to be its ancestor's phenotype, phi 1, plus some deviation delta 1, 1, okay? And we can always do this if you think about it, right? Because if you can always define delta as the difference between phi 1, 1 and phi 1, which you both measured, right? And then delta 1, 1 is just the difference between them. So then phi 1, 1 is phi 1 plus delta 1, 1, okay? So more generally, phi ij, so the jth descendant of the ith individual, ith ancestor, is phi I plus delta ij. Okay, so this is just notational sort of convenience, okay? And then the last thing we want to define is what we're going to call fitness, which is how many descendants are assigned to each ancestor, okay? So, and we're going to call fitness with W. So W1 in this case is 2, W2 is also 2, and W3 in this case is 1. Okay, so the first ancestor has 2 descendants assigned to it, so has 2 offspring, has W2, W1 is equal to, W2 equals 1, also equals 2 in this case because there are also 2 descendants for the second ancestor, and W3 is 1. The third ancestor only had one descendant. Okay, so now we're going to write down phi bar. So this is the ancestor mean phenotype, and it's simply 1 over n. N is the number of ancestors. Okay, times sum over all the phis. Okay, sum of all the phis. Okay, and the descendants mean phenotype is type is phi bar prime, let's call it, right? And it's 1 over n prime, which is the number of descendants, which is different than the number of ancestors, right? In this case, it's 5 instead of 3, right? And then sum over, well, because now we wrote down descendants with 2 indices, right? We have 2 subscripts for denote each descendant, right? We need to sum over both subscripts. So sum over I and j, okay? So the ith ancestors, jth offspring, okay? So this sums over all the offspring of the ith ancestor, right? Well, first of all, sums over j, okay? And then sums over all the ancestors. So this double sum sums over all the descendants here, okay? And then you divide it by the total number of descendants, okay? And the total number of descendants, actually, you can write down as simply is the total number of sort of the total fitness, right? The sum of the W's, okay? So in fact, you can write this down as Wi, sum over I, Wi times sum over I and j phi I j. Okay, so I mean, things start getting like more sophisticated and fancy when you start, you know, writing down sigmas and sums and indices and so on. But all we do here is summing. Okay, there's nothing fancy going on really. And then one last thing we can do for the sum is we can express it using this decomposition. Okay, so using this the idea that each descendant can be its ancestor phenotype plus some deviation. Okay, so then we have 1 over Wi, sum over Wi, sum over I, sum over j, and now it's phi I plus delta ij. Okay. Again, I haven't done anything. I haven't given you any new information. I'm just writing down. I'm just playing around with different sums, essentially, that all add up to the same thing. Okay. There's nothing new going on here. Okay. So what we want is we want phi bar prime minus phi bar, okay, which we're going to call delta phi bar. So this is the change in the mean fitness from one generation to the next, from the ancestor to the descendants. Okay. So and that is so phi bar is 1 over n, or actually, so whoops. Phi bar prime is 1 over I Wi. These two sums, sum over I and sum over j, phi I plus delta I j minus 1 over n phi I, sum over I, phi I. Okay. So first, one thing we can do is, so this is the sum of all the fitnesses. This here in the denominator. This thing is, you can write these things as n times W bar, okay? Because, you know, W bar is defined as 1 over n sum over I Wi, right? So then if you multiply this by n, you get n times W bar, which is this sum here, okay? So the advantage of doing that is then we have 1 over n here and here, okay? So you can factor out that Wn, 1 over n, okay? And the next thing, okay, and the next thing you can do is, so the next thing you can do is, so you will have n W bar. Now the next thing you can do is, you have phi I here in a sum over j. So phi I, the ancestor's phenotype, doesn't depend on which descendant you're looking at, right? It doesn't depend on j. So you can actually take phi I out of this sum and then leave the sum over j only for the delta one. The only thing that you have to do is, you do have phi I j times, okay? Or however many descendant each ith offspring is. So you need to multiply this with Wi, okay? So you can write down, so you can take this phi I by multiplying it with Wi, because this is j equals 1 to Wi actually, okay? And this is I equals from 1 to n, okay? So you can take out this phi I by just multiply with Wi, because it doesn't depend on j, and then take it out. and then you have j over j from 1 to Wi delta ij here, okay? And then you do have to sum this over all the i's, okay? minus 1 over n phi I delta I, or phi I, sum over I delta phi I, okay? And so now we're getting somewhere actually, because so let's say we did this. So let's say we factored out 1 over n times w bar, okay? And then we divided the sum into 2. So we have I, wi, phi I. So we divided this sum into 2 because you can, this is, I mean, summation operator, just, you can just distribute that. So you can sum this separately from this. So I take this part, okay? And there's a 1 over n times w bar in front of it. And then I'm gonna also take this part and also factor out with this, but this only has 1 over n in front of it. But if I add a w bar, then I can, in front of this, if I multiply this thing with w bar, then I can factor out 1 over w bar. So in fact, I can write this as minus w bar over phi I. And then what I'm left with is this term, which I don't have space to write, so I'm gonna kind of shift things over a little bit. What I'm left is this second sum, 1 over n w bar, sum over I, sum over j, delta ij. Okay. So, okay, so I'm almost done. So now I have this 1 over n times the product, okay, sum of the product. So in fact, I can write that as sum over wi, or I can write that as, maybe the expectation notation is actually useful here because it reduces ambiguity. The expectation of wi times phi I, and then I have 1 over n times sum over phi I, which is the expectation of phi, minus expectation of w, which is w bar, times expectation of phi. Okay, let's put the I as well, and plus this, whatever this is. Okay, this is ij delta ij. Oops. Yeah. Okay, and this should look familiar to you from the previous hour, right? This is the expectation of the product minus the product of the expectations. So this is the covariance of w and phi. Okay. But what is this? What is this last term? So did I forget something about the last term? I don't think I did. Oh yeah. So what is this last term? So this last term is we're gonna do a little bit more surgical. So first of all, let's write this term. So delta phi bar, and in fact, let's put this w bar on the other side. Let's multiply everything by w bar here. So just get rid of this w bar on the denominator. So w bar times delta phi bar is the covariance between wi and phi I plus this is going to be some sort of expectation, but we'll see what it is, and just we need to do a little bit more surgical algebra there. It's the sum over I and j of delta ij. Okay. And any guesses? What did I forget? I always forget something in these derivations. So one thing we can do here is, so this is all the deviations of the offspring from their parents, right? So delta ij, this is sum over all of those derivations. One way we can express that is you can take the mean offspring, mean deviation from the offspring from their parents. Okay, so we can define delta bar I, okay, as sum over 1 over wi, which is the number of offspring of ith individual, times sum over j delta ij. Okay, so this is basically the deviation of. So if you take a look at this first ancestor only, right? Then you can calculate the mean deviation of the deltas, mean of these deltas of its offspring. Okay, so for example, if the phenotypes were, for example, perfectly genetically determined, right? There was no mutation or whatsoever, and they're perfectly determined by genetics, then, for example, that mean they have a perfectly determined they have a genetic component, but also have an environmental variation, for example, then the environmental variation, if it's unbiased, then delta i's might end up being sort of washing out. Okay, so the average delta might be 0. Okay, or if the trait is literally the genotype and there's no mutation, then each of the descendant traits might be identical to the ancestor traits. So all of the deltas might be identically 0. So therefore the mean delta will also be 0, okay? But you can also imagine that the delta, for example, being the phenotype being, for example, salary at age 30 for a human population, okay? And even if everybody has the same profession as their parents, because of inflation, their salary will be higher, right? One generation later, right? So even if nothing else changes, because of inflation, the money units have changed essentially. So therefore delta will be positive, okay? So this delta is basically the mean deviation of the offspring from their parents, okay? Measured for each parent, okay, this delta I bar, right, is measured for each parent I, for each ancestor I, okay? and then you can write down this delta, this sum over j, simply by the definition of delta I bar. This sum over j is essentially delta I bar times wi. Okay, so now delta I bar is an individual level measure for the ancestors, right? It's defined for each ancestor I. There's a defined delta bar, and you multiply with wi, and you get this sum by definition. Okay, so now this last term becomes, and this is basically what the price equation is, that with that substitution, you get the price equation, covariance of wi and phi I plus the expectation of delta bar I wi. Okay, so that's the price equation. And I'm gonna highlight it in red. Okay, so what does this mean? So again, before we talk about what this means, all I did in all this derivation here, right, from here to here, I described you a situation where I have two populations, ancestors and descendants, and the only real information is in these sort of mappings from the ancestors to descendants, and and then I also gave you all the trait values of all the individuals. Okay, we measured all of that. All of that information is in our books before we write down the price equation. And when we write down the price equation, we just essentially we wrote down the mean fitness or the mean phenotype of the descendants. We wrote down the mean phenotypes of the ancestors. We took this difference, and then we just did algebra. Right? We didn't do anything. There's no new information in the price equation. All of the information was already there before I wrote anything down about with the price equation, because I gave you all the phenotypes, and you could just as well calculate this and this, take the difference, and you're done, right? You get the same quantity as you get from the price equation. Okay, so so why do we do this whole rigmarole? Well, the reason we do it is the price equation sort of chops up this sort of change in the mean phenotype into different bits. Okay, it partitions it into different bits, and this is how it partitions. So this is this is remember, the covariance is gives you the relationship between two different variables, right? So if I have a population where the phenotypes are like this and the fitnesses are like this, right? If the covariance is positive, that means individuals with higher phenotypes values leave more offspring. I mean, they get assigned more descendants, right? So that sounds like natural selection, right? Because natural selection is the idea that if you, for certain genotypes or certain phenotypes, leave more offspring, and therefore that changes the mean phenotype of the population, right? And what does the price equation say? Well, it says if the covariance is positive, then that's going to make this delta phi bar more positive, right? Because you get, because W bar is a positive number, right? So the covariance contributes positively to the change in the mean phenotype. So that's basically an expression of natural selection. Okay, so sometimes people call this covariance term selection term in the price equation. Okay, there is a little subtlety, because if you think about natural selection as a deterministic process, well, we tend to think about natural selection as a deterministic process. And if it's deterministic, yes, this is just natural selection. But in fact, in nature, fitness is stochastic, right? It's like sometimes individuals with good phenotypes or sort of more fit phenotypes have bad luck and they have low fitness. Sometimes individuals with sort of bad phenotypes have good luck and have high fitness, and so on. So any given population, again, this is a realization of the sort of ancestor-descendant relationship. Any given pair of population is going to be sort of the realization of the stochastic process. So therefore, in fact, this covariance term also incorporates the chance, essentially, that went into determining those fitnesses. So, and you can actually, if you are really serious about this, you can write down the stochastic price equation, where you actually like take the expectation over these covariances, and that really gives you the sort of the expected natural selection. Sean Rice has several papers on this, but for our purposes, we're just going to call this the selection term, because it sort of gives the idea that the change in mean phenotype is given by sort of covariance between fitness and phenotype, plus, and then there's this term. Okay, this term is hard to understand. Okay, or it's sort of subtle and kind of, actually, it's sort of it has a subtle meaning, to the extent it has meaning at all, because the way we define this delta bar is we measured all the deviations. We expressed all the offspring phenotypes as deviation from the parental phenotype, okay? And then we took the mean, okay? And now this term is the expectation of the product of that mean with the fitness of the parent, okay? So that's sometimes called the transmission bias term, okay? So this is sometimes commonly called actually transmission bias term. But it actually can account for a lot of different things. So this is called selection term, which is, again, it's commonly called selection term, and I'm going to put it in quotation marks because, again, there's an effect of stochastics there too. This transmission bias term, though, it can be affected by lots of things. It can be affected by imperfect inheritance. So, for example, if heritability of a trait is low, that term is going to be potentially be higher. It can be affected by environmental change. Okay, for example, like I said, like in the salary example, even if everybody perfectly inherits their parents' profession, in a human economy, then in the presence of inflation, their salary is still going to be higher, right? Even if everything else in the society, in the economy, stays constant, because basically money units have changed, right? So that will introduce a positive transmission bias, okay? And to give a more biological example, for example, if you have, and there's an example of this with like marmots, for example, if you have a warming environment, if the mean temperature in the environment is going up, and individuals awake from hibernation earlier because of that, right? Even if there's no genetic change in the population, because individuals are active for longer, they might grow fatter. Okay, they might eat more and have become bigger, right? So there's, you know, secular environmental change in that kind of cases, okay? That can contribute to transmission bias. But the point of all this exercise is you can partition changes. You can partition the gross change in the mean phenotype, delta phi, into all of these different components, okay? And this is not the only way you can partition it. You can partition it in many different ways, and we're gonna actually see some additional ways relating to social evolution. But the price equation gives you sort of a recipe or a group of recipes to partition things, okay? And then once you partition things, then you can basically say more, you can make informed commentary about, well, this pathway, this, you know, for example, the transmission bias term is more important in this population than the covariance term, for example. And that might tell you something biological, okay? Is that clear? That's the whole reason we do the price equation. In fact, that's actually one reason we do the price equation. There's other reasons too, because turns out that all of this derivation was done like basically as an algebra after I've given you, after the fact, after I've given you all the phi's and w's and so on. But in fact, you can also write this in a sort of in a sort of model population, where if you have a model for what gives fitness, okay, what determines fitness as a function of phenotypes, then you can write down the price equation in that model population, okay, using some sort of modeling assumptions, but then you actually do make some assumptions about the population, right? But you can use those assumptions to write down the predicted evolutionary change if you have a model for fitness. Okay, so you can also use price equation as a predictive framework in that way. Okay, if there's any questions about this? Okay. One practical note is that it's important not to forget this W bar here. So both of these terms are, you know, you can either put W bar here, which allows you to write this in one line, or you can basically divide both of these terms by 1 over W bar. But whatever you do, it's important to not forget about it. Okay. Good. So what can we do with the price equation? Well, so let's do Hamilton's rule, okay? And so Hamilton's rule as derived from the price equation. And I do this, I'm gonna do this here. Yes, there's a question about transmission bias. You can ask it, Matt. Can we say that value would increase with further generations? What do you mean by further generations? You can unmute and ask if you want, by the way.
Sure, please unmute and ask.
Could that be? Okay, well, let's talk about it after I derive Hamilton's rule, maybe, because I think you might be getting ahead of ourselves. So the question is whether the transmission bias term can increase with further generations. Well, let's get back to that. If offspring are male and females, and phenotype change is positive for females and negative for males, does everything cancel out? Is it working with nonlinear relations? The answer is it may cancel out, right? So yeah, I mean, basically, if you have equal numbers of males and females experience, you know, a given phenotype change on average, and males experience the exact same phenotype change on average, but the opposite sign, then they will cancel each other out. The way that would show up in the price equation would be, I mean, it depends on what causes the males and females to differ in phenotype. So if some, for example, if some parents only produce males, for example, like the Travers-Wheeler type hypothesis, where, you know, like some parents have high male fitness and they only produce males, and their male phenotypes are biased because of that. And some parents only produce female offspring and their female phenotypes are biased in that way. Then that would show up in the transmission bias term. Or it could also show up in the covariance. So then the covariance term and the transmission bias term might counteract each other, and the mean phenotype might change, might be 0. So for nonlinear relations, it depends on what nonlinear relations means. Nonlinear relation between fitness and fitness and phenotype, or. But in general, this is all of this is. I mean, I didn't make any assumptions about linearity of any relationship here, right? Because I didn't make any assumptions at all in deriving this. So this all works with nonlinear relations between fitness and phenotype, or fitness and transmission, or whatever, right? As long as you calculate these quantities, you can calculate these quantities. These quantities give you the mean phenotypic change, basically. Okay, but in fact, that's actually a pretty good segue to to the next segment, which is the Hamilton's rule. So where we are going to actually make an assumption of linearity. Okay, so Hamilton's rule is so to derive Hamilton's rule, let's specify the social interaction, and let's go back to the slides. Actually, think back to the slides where you have two individuals, okay, that are interacting with each other, okay, and one individual has, we're going to call it genotype 1 and genotype 0. Okay, so these are our A's and B's essentially. And then ones give a benefit B to the others and pay a cost C. And then the zeros just give 0, okay, and pay a cost 0, right? So then, so if your genotype is 1, genotype 0. So if you interact with 1, 1, if your genotype is 1 and you interact with another one, you get 1 plus B minus C. If your genotype is 0 and you interact with genotype 1, you get 1 plus B. If you're genotype 1 and you interact with 0, you get 1 minus C. And then if your genotype is 0, 0, then you get 1. Okay. So this is sometimes called the donation game. Okay, and it's a donation game because you donate a sort of a benefit, something that's worth B to the other one, and that's, to you it's worth C, so you pay a cost minus C, okay, or you pay a cost C and then benefit someone else. It's also called an additive prisoner's dilemma. This is also the additive prisoner's dilemma game. Okay, and additive, the prisoner's dilemma because historical reasons. Additive because you can write down the fitness of each type, or the payoff of each type, as a sum of something that only depends on its own genotype, which in this case is B, okay, or sorry, which in this case is minus C, right? Whether you pay minus C or not is only a function of your own genotype, plus something that depends only on the partner's genotype, which in this case is B. Whether you get B or not depends only on the partner's genotype, okay? In the non-additive case, you can also have interaction effects. Like, for example, if both of them are 1, 1, you have another term, for example, or if both of them are 0, you have another term, or something like that. So that would be the non-additive case. But this case is additive because you can just write down, the fitness before, you can write down all of these entries as a simple sum of something that only depends on genotype, the row and the column, okay? And which turns out to be kind of important, okay? And the reason so the reason I sort of labeled one of the genotypes 1 and one of them 0 is going to be apparent now, because that lets me actually write down the phenotype in a simple way. So now I can basically say the phenotype of I is a genotype. Okay, so it's 1 if sort of if cooperator, which is donates B, pays a cost C, and it's 0 if defector, which is doesn't donate, no donation, no cost. Okay. So now so now the phenotype is the genotype, okay, which is going to make things slightly easier, because now if we assume mutation, if we ignore mutation, then the phenotype of offspring is going to be the same thing as the phenotype of their parents, because it's their genotype, okay. And we're going to assume haploid genotypic haploid genetics here. Okay, so now you can summarize this matrix basically as, so if individual I's, so you can summarize this matrix by writing the individual I's fitness. So if these are the fitness values, okay, so individual I fitness is 1, so everybody gets this 1. That's like the baseline fitness, okay. You only get the benefit B if your partner has genotype 1, okay. So if your partner is J, for example, if the focal individual is I, okay, and the partner is J, okay, you only get that benefit B when your partner is of genotype 1. So when your partner's, so if you just multiply B with phi J, then you're done. Then you account for that, because if phi J is 1, then you get that B, and phi J is 0, then you don't get that B. And then you pay this cost C, but only if your own genotype is 1, right? So if your partner's genotype J, phi J is 1, you get this benefit B. If your own genotype is phi I is 1, then you pay this cost C. So now you can, and this is why it means to be additive, right? This is what it means to be additive, because you can write down the fitness, and you can basically, you can verify that this WI corresponds to these entries here, right? So this is phi J equals 1, phi J equals 0. This is phi I equals 1, phi I equals 0, right? So now this is a linear model of fitness, okay? So this is where, because fitness is a linear function of phi I and phi J, fitness of I. Okay, so and it's important to note now, I have made up this model, right? This model now is based on assumptions about how the social interaction proceeds, right? So I mean, in real life, ideally, right, I would have to actually make sure that there is actually a benefit B being paid and like being provided, and measure that benefit B, and there's a cost C and measure that cost C, and so on, right? So those things are, so now I'm actually like building a model based on the behavior, okay? I'm not doing what we did for driving the price equation. I'm not saying these are the actual fitnesses that were realized. I'm saying this is the expected fitness in effect, based on the phenotypes, based on what I know about the behavioral interaction. Okay. But now I can actually, once I make this model, if I feel confident about this model, now I can plug that into the price equation and use the price equation in the second way that I was talking about, right? I could use the price equation as a predictive model, okay? And so in fact, what I can write down is W bar times delta phi bar, which is now the delta G bar, if you will, like the change in the genotypic frequencies, right? Is the covariance of WI phi I plus this transmission bias term. Okay. Now though, if 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 phi is the genotype and there's no mutation, then all the offspring genotypes are the same, is going to be the same as their parents' genotype. So delta is always going to be identically 0. So I'm just going to ignore this. Okay, I'm going to ignore the transmission bias term. That's why it's called sometimes transmission bias, because if you have perfect transmission of the phenotypes, then that term that vanishes. Okay, so now I'm basically, the only thing I need to calculate is this covariance. Okay, and the covariance, so Wi is now given by this, right? So I can just substitute that into my covariance, for Wi into my covariance. So it's 1 plus b times phi j plus or minus c times phi I and phi I. Okay, so again, the covariance is simply an expectation or simply an average, right? So I can distribute that over a sum, right? So I can basically write this as the covariance of 1 and phi I plus the covariance of b times phi j and phi I plus the covariance of minus c times phi I, phi I. Okay, so then another useful property of the covariance, which is, if you go back to the definition of covariance, should be obvious. You know, if you multiply any of these numbers by a constant, that's the same for every x and y, right? For every measurement. So if you put like an a times x here, then you'll have an a times x minus a times x bar. So you can factor that out and then factor out of the sum because it doesn't depend on I. So then, so a times x, covariance of a times x and b times y is simply a times b times covariance of x and y. Okay, so when a and b are constants. So basically you can pull out the constants from the covariance. Okay, meaning that since this b and this minus c are constants, we can pull them out of the covariance. And of course, here this one is a constant itself. And by definition, the constant does not covary with anything, right? And therefore that covariance is 0, right? So that covariance is 0. And then this covariance is b times covariance of phi j, phi I, plus or minus c times covariance of phi I, phi I. And obviously, again, from the definition of covariance and the variance, right? So if x is y, x is equal to y, right? The covariance of x with itself is simply xi minus x bar times xi minus x bar. So xi minus x bar squared, which is the variance, right? So the covariance of something with itself is the variance. So this is the variance of phi I. And then as a last step, what we can do is we can factor out the variance of phi I. And then what we have is b times the covariance of phi j with phi I divided by the variance of phi I, right? Because we factored that out, okay? Which we defined before as the regression coefficient of j, phi j over phi I, minus c. So this whole thing is equal to phi bar over delta, w bar over w bar times delta phi bar, okay? So in this equation, the variance is always some non-zero, non-negative number, okay? So it's good. And then if there's any variance, it's always going to be positive. W bar is always some positive number because negative fitness doesn't make sense, right? So it's either 0 or something positive. And so then for the sign of delta phi bar, whether the mean phenotype, in this case the mean genotype, will increase or decrease, is entirely determined by the sign of this parenthesis, right? Because everything else is positive. So therefore, delta phi bar is greater than 0 if and only if b times beta phi j phi I minus c is greater than 0. Okay. And this is the kicker here, right? What is this beta? This is this regression of the ith individual's partner, J, the partner's genotype or phenotype, or in this case, genotype on the partner itself, partner's phenotype itself. So this is basically how much the partner looks like the focal individual. Okay, or in the using the definition of regression, if you change the focal individual's genotype from 0 to 1, from a non-donator to donator, how much does on average, how much does the partner's phenotype change from donator to non-donator, from non-donator to donator? Okay, and that measures basically how much more likely donators or cooperators are like to be interacting with other cooperators relative to defectors interacting with cooperators. Okay, and that's effective. That's sometimes called and that's effectively what a very general definition of relatedness. Okay, and sometimes it's called a regression definition of relatedness, because it's basically measures on average, not necessarily identical by descent, but identical by state. On average, how identical are the interacting parties to each other, whether in terms of their genotype in this case, or more generally phenotype. Okay, so that basically is a measure of assortment. And then if you call this R, then what you get is B times R, or R times B minus C greater than 0, which is, of course, Hamilton's rule. Okay, and the important thing to note here, and I'm going to stop in a second, the important thing to note here is that we derived this rule, basically. I mean, we basically just wrote down, this transmission bias term vanished, right? So the only thing that this rule comes from is from this covariance term, right? So if this number, if this equation, if this quantity BR times minus C is positive, then this covariance is positive. Okay, if it's negative, then the covariance is negative, meaning that, and remember, phi is 0 if you don't donate, and 1 if you do donate. So if the covariance is positive, that means that the donators or the cooperators, right, have higher fitness than defectors. Okay, so then Hamilton's rule actually is an expression of the fact, if Hamilton's rule holds, right, if B times R minus C is greater than 0, that means that cooperators or altruists have higher fitness on average than non-altruists. Okay, why do they have high fitness? Because for this to hold, right, because B and C are both positive, for this to hold, R has to be big enough. If R is 0, right, if this regression coefficient is 0, meaning that this covariance is 0, right, then this cannot hold, right? But if R is big enough, that means that cooperators interact with other cooperators often enough that the benefits from cooperators tend to flow to other cooperators, okay? And therefore, cooperators as a group, on average, have higher payout, okay? So that's sort of important to keep in mind, because sometimes you see in textbooks, and we have text, for example, that, you know, Hamilton's rule says, like, if you pay a cost, if you help relatives, then you may, the altruism still evolve, which is true in a sense, but in a sort of subtle sense, because Hamilton's rule actually is an expression that the individuals who pay the cost minus C, on average, get more than enough of the benefits back. So therefore, they're better off at the end of the day. Okay, in the simplest model, you can build other models, but where, for example, with class structure in, you know, ant colonies and whatnot, where you don't get any of the benefits back, but that then selection only will favor them if, for example, the reproductive values of those classes are nil, right? Okay, so I'm going to stop here, and we're going to talk about some